What's up, everyone? This is LeetCode 543, diameter of binary tree. We've done this problem in Python. Now we're doing it in C++. So given the root of binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges between them. So, yeah, from one node to the next, right, this edge counts as a path. So, right, this would be, this would count as a length, this would count as a length. So we're just basically have to find the longest path, essentially. Now, this problem is similar to a problem called balanced binary tree that we've done before, in the sense that we have to work bottom up rather than top down, just because it simplifies the problem and we have less overhead between the checking. Because if we start from the top, we can check the paths from this node, then we go down and check the paths from this node, and it's just too much overhead. So we want to work bottom up so we can kind of reuse information from nodes below where we were. So the way we're going to do this is we're basically going to go bottom up, okay? And as we go bottom up, when we're at a specific node, we're going to add the left and the right paths, and we're going to check, okay, when we add the left and the right paths, at a given node, the paths from the left subtree and the right subtree, does that length, that total length, which would be the diameter, is that greater than the max diameter we've seen so far? If it is, we can update the max diameter. And then as we go up, we add 1 to our diameter, because obviously a edge is considered a path, right? So we increase the length by 1 when we go up. So what we would do when we go up is we basically take the max from the left and the right that we've seen so far, whichever one's longer, and we add 1 to it. For example, imagine this 4 had a node that was down, right? Another node down here and another edge. When we're at this 2, right? The max diameter we've seen so far is 1, 2, 3, right? If we had another node out here, it'd be 1, 2, 3. Okay, that's the longest diameter that we've seen so far. It would be 3 at this 2. Now, when we go up, though, we add 1 to the max length that we've seen so far from the right and left subtree. In this case, the longest we've seen is 1, 2, right? And so the new longest path would be 1, 2, 3, 4 now, okay? And so that would be the max diameter we've seen so far. So as we go, when we're at a specific node, right, because we can go, right, like our path can go like this or like this, we just add the left and the right. When we go up, though, we add 1 and take the max from the left and the right, because when we're going above, right, obviously our path can't include the left and the right subtree and also go up here, right? We can't go like down here and somehow get to this 1, right? So that's why we take the max of the left and the right as we go up, okay? So we're going to make a variable called int max diameter, right? And we need a DFS function because we have to work bottom up. So we need to get to the bottom of the tree. So we're going to pass this a tree node, root, okay? Of course, we need a base case, right? So that we don't run into problems. Okay, so if root is null, right? And we're going to go all the way to the bottom of the tree. And when we hit the very bottom, we're eventually going to reach the child nodes of these leaves, and they're not going to have children. So we just return 0 in that case, right? Okay, now we need to keep going all the way to the bottom. So we're going to say int left is equal to DFS root to the left, int right, DFS of root to the right. And again, if you prefer Python, I've done this problem in Python, but here's where we set the max diameter. So we're going to say max diameter. We're going to do standard max of the max diameter, right, and the left plus the right. If the left plus the right path of a given node, right, like for example, if there's 2, right, if we can go like this, and that's the longer than the max diameter, that gets set as a new max diameter, which is the case, by the way, initially, because max diameter is 0, right? So when we go something like this would be 1, 2, which is, so the new max diameter so far is 2, okay? So just showing you what we're doing. Now, when we return, though, we would do 1 plus the max of the left and the right subtree, right? Because let's say we're at this 2 and we go up. If we had another node 4 and down here, right? Well, it wouldn't make a difference. It'd be 3 either way, because we could go 4 up to 4, 2 and 5, so it'd be 1, 2, 3, or we could go up to 4, 2 and 1, right? But then we can include this 3, so it'd be 1, 2, 3, 4, and that'd be the new max diameter. So again, this and this are doing different things. This is basically finding the max diameter of a path that includes the current node, whereas this is passing the max path between the left and the right subtree and adding 1 to it, because we have to include this node now, right? So basically, is this path longer or this path longer, right? Whichever one's longer, we use that, and then from there we calculate the new max diameter with the left subtree and the right subtree. Okay, that's all we're doing. So pretty simple. So down here, we're going to say press.root, right? And after that runs, we just return the max diameter. So yeah, if you don't understand this problem or how to work bottom up, balanced binary tree is another problem that is pretty similar in nature. Not exactly the same, but it's very similar. So that's another problem you can practice as well. But yeah. Anyways, I hope this helped. I think I explained that well. Like, I don't think this is an inherently like a difficult problem. You just need to understand how we're calculating the maximum and how we're accounting for the left and the right subtree of, and accounting which one's the longest as we move up the tree, okay? But I hope this helped, and I'll see you in the next one.